Excellent. Hello, everyone. I am Brian Lorenz. I'm a final year grad student at Berkeley. And I'm very excited to share with you what I've been working on for the past 5 years, studying dust in the MOSDEF survey. So first of all, why do we care about dust? It's very important to how galaxies grow. It's formed in stars, spread throughout the galaxy. And it also really affects our observations of galaxy properties. So here is an example SED in blue with no dust and in orange with dust. And you can see it sort of decreases the flux everywhere, and especially at blue wavelengths. And if you tried to make measurements without accounting for this dust, your properties could certainly be incorrect. And in the local universe, it's pretty, we can see the dust lanes in the galaxies, figure out where the dust is distributed. But at redshift 2, that's much harder. And so some possible geometries that have been proposed is sort of just the ISM doing most of the attenuation. Maybe it's in the star-forming regions and throughout the ISM. Or maybe it's sort of patchy in clumps throughout the galaxy. And so my job has been to try to figure out what dust looks like at redshift 2 and how it's affecting all of our measurements. So to do this, I've been using the MOSDEF survey, which is comprised of some wonderful spectra from Keck, all sort of around redshift 2, and it contains 1,500 galaxies. So we have these excellent Keck spectra with emission lines, and in particular, the H alpha and H beta lines are very sensitive to dust. So if you normalize the H alpha fluxes to each other, you can see the H beta line, sort of its relative flux to H alpha, is controlled by the dust. And so looking at this Balmer decrement can tell you sort of how much dust there are in these galaxies. You can get another measurement from just photometry. So that was sort of what I showed at the start of this talk. You can fit an SED with a model, and that can give you a dust measurement. And lastly, for this work, we needed axis ratios, sort of how inclined the galaxies are. And so from HSC images, we can get how tilted these are. So for the first portion here, I'm going to skip all the analysis and share some results. We basically took galaxies and split them into groups based on their axis ratio, whether they were edge-on or face-on, in different mass and star formation rate bands. So here I'm showing the Balmer decrement, so that's a measurement of dust, versus mass. Points are color-coded by star formation rate, and the face-on galaxies are stacked in circles, and the edge-on ones are these ellipses. And you can see a little bit surprisingly that whether a galaxy is face-on or edge-on does not affect the Balmer decrement across most of these groups. We looked at this again for the photometric AV measurement. So this comes from the SEDs. And a similar trend where edge-on versus face-on had the same dust attenuation. And we also noticed in general that this photometric AV was lower than what we get from the Balmer decrement. We'll revisit that later. But what did this mean? So what we thought about this for a bit. We were a little puzzled at first. And I think the conclusion we came to is that the ISM is not a significant attenuator. So if the dust attenuation was happening in this ISM, and these are all disk galaxies, if you look at one edge-on, you'd be looking through more dust in general than a face-on galaxy. But we're not seeing this difference. So if we remove the ISM and instead make the attenuation happen just local to the star-forming regions, then these are pretty spherically symmetric, and it shouldn't matter which orientation you're looking at the galaxy. So this is where we sort of ended after my first paper, and you can certainly check out those results. But then where do we go from here? It would be great to get individual dust measurements of galaxies, but unfortunately, that's not possible for all of them. The H beta line can get very faint in dusty galaxies or low mass ones. And so we can improve on this by stacking. But instead of stacking sort of by axis ratio that we did before, we're now going to stack by SED shape. And there's a lot of properties buried in the galaxy SED that stacking in this way can let us probe dust across evolutionary stage and things like that. And importantly, we know that axis ratio doesn't really matter. So you can stack edge-on things and face-on things in the same group. So how did we do that? First, we need to identify what it means for two galaxies to have the same SED shape. And so we wanted to do this in sort of a mathematical way. So we take the galaxies We move them to the rest frame, smooth out their SEDs into these filters so we can compare them, and then run a cross correlation for the shapes of these galaxies and get a similarity value from 0 to 1, where 1 is perfectly identical and 0 is perfectly anti-correlated. So we do this for every pair of galaxies in our sample and end up with this giant similarity matrix where every galaxy is compared to every other one and has this value from 0 to 1 about how similar their shapes are. We run a clustering algorithm on that splits the galaxies into 20 groups based on these values. And then once you have galaxies in the same group, such as these two, you scale them up to sort of the same height. Do this for all of the 20 or so galaxies that might be in that group, and then can form a composite SED as the median of these points. So these have been great. It's sort of a model independent grouping. We're not assuming anything about their mass, their star formation rate. All we're assuming is that they have similar SED shapes. And as I was saying before, these SED types can span various evolutionary stages. You can get high mass groups that maybe are starting to quench their star formation. You can have maybe starburst galaxies that would all have a similar SED. And these have a very broad wavelength coverage. You can see they're more highly sampled than a normal galaxy SED, and you can even see some emission lines poking out. So just to give you an overview of the data set I'm working with here, these are composite SEDs on the left, and then they're stacked spectra on the right. So we took the Keck spectra from all of the galaxies in this group and stacked those as well in a similar manner. And these are sorted by mass. And the spectrum on the right just is normalized for visualization to have the same H alpha line. And you'll see as we get to the higher mass groups that H beta is going to start to drop, mostly due to dust. You can see a wide range of SED shapes. And especially as we're getting to these higher mass galaxies, H beta is starting to disappear. So before we talk about the dust, a quick overview of the sample. We have 20 composite groups. They span a wide range of masses and star formation rates. They mostly follow along the star forming main sequence. And you can see a couple of groups are represented with squares here. These are ones where even with the stack spectra, we couldn't detect their H beta lines. And so we couldn't get a perfectly accurate dust measurement. We can place lower limits on their star formation rate. And for those who are familiar with the UVJ diagram, here they are in UVJ space. These are color-coded by mass. You can see mass and dust attenuation tends to increase up that sequence on the UVJ diagram. And we selected for star-forming galaxies, which is why none are in the quite same region up there. But most importantly, what does this say about the dust? So we measured Balmer decrements for all of these groups from the stack spectra and plotted them versus mass and star formation rate. And both show a pretty strong correlation and are largely consistent with previous works and stuff. We also use those composite SEDs, fit them with cross-vector, and got a photometric dust measurement. Again, plotted with mass and star formation rate. There's certainly a strong correlation with mass and a fair one with star formation rate. But as I said earlier, the Balmer decrement AV is higher than the stellar AV. So this is looking at the AV difference. And that correlated quite well with star formation rate and maybe a little bit with mass. So taking this all together, how do we reproduce these trends without the ISM being a strong contributor to dust attenuation? Because as from the start of this talk, edge-on or face-on galaxies are showing the same dust properties. So first, stellar and nebular AV increase with mass. Well, that's pretty easy to do if you just make the star-forming regions more dusty. If all the attenuation is happening in these regions, if you add more dust, then that will increase both of the AVs. But there's this AV difference that needs to be driven up, where the nebular attenuation increases in these high mass and star formation rate galaxies, but the stellar AV does not. And for that, we propose star-forming clumps or central starbursts, or any sort of dense regions of star formation that are going to have higher dust attenuation. And if these are forming lots of young, hot O and B stars that are producing lots of nebular emission, and then going through a very dense, dusty region, that'll drive up the nebular attenuation without affecting the stellar attenuation as much. So this is at least my current model and understanding of dust at redshift 2. But where do we go from here? So my current project is using JWST to try to visually map the dust distribution. And so we started making these H alpha maps. Of course, this is still work in progress. And hopefully can make a similar map with the passion beta line. And then similar to taking a Balmer decrement, we can do an H alpha to passion beta decrement and hopefully map out the dust. So look forward to this in the coming months. I will leave up my summary. You can find these in my past 2 papers. And yeah, thank you. I'd be happy to take any questions.